Okay, we're back. Good day. Today we're talking about mixing strong acids and bases together. Now, you learn in previous years that when you mix an acid and a base together, they neutralize each other. And so, yes, that is true. They do neutralize each other. However, getting it perfectly neutral is more complicated than that because it depends on the strength of each acid and base. Remember that there's something important that maybe you might get confused with, and that is when I talk about the word strength of acids and base, it doesn't mean the concentration. So concentrated and dilute, that's talking about how much of the acid is dissolved, whereas strong and weak acid does not necessarily mean that. Strong means that it really favors the products, and weak means that it's an acid in equilibrium. So you can have a very concentrated weak acid, and it's still quite dangerous. And you can have a dilute strong acid that is not very dangerous. Like you could take hydrochloric acid, make it very dilute, and even though it's considered a strong acid, it would not be quite dangerous. So don't think about concentrated, dilute, strong, and weak as meaning dangerous. You have to sort of realize that strong and weak mean, is it in equilibrium or does it go 100% forward? Because a weak acid will stay in equilibrium, whereas strong will just push 100% to the products. Anyways, they neutralize each other, but the resulting solution will be neutral if the original moles are equal. So you take the moles of the acid and the moles of the base and figure out, well, not just the moles of the acid and base, but you have to figure out the actual concentration of ions in solution and try and see if those are equal, because it's only if H3O and OH are equal that it'll actually be completely neutral. So if you added a little bit too much acid, the solution will then be acidic. It'll push it past its perfection, its perfect Kw point, and if you where the concentration of each are equal. And if you had slightly more OH, then it will be basic. And so today we're going to be looking at figuring out, hey, what's the pH of the final solution if we mix together a bunch of stuff? Okay, so we're going to be using dilution calculations, obviously. Here's the example number 1. We have 125 mils here's a certain concentration of a strong acid. Okay, so that's a moderate, actually it's pretty not weak, I shouldn't say, a dilute concentration of a strong acid. Okay, and here we have a 75 mils, again a more concentrated, the concentration is higher, and NaOH, which is another strong base. So here we're combining two strong bases. And we're just going to basically do a dilution calculation to figure out what the final concentrations are of these. So first, let's figure out what the final concentration of HCl is. And so again, we do dilution concentrations. Here it is, the hydronium concentration, because it's strong, is equal to the concentration of HCl. So that was given to us in the example. We dilute it, and we find that that is this number. Okay. And then we do the same for the OH now. Okay, so again, the concentration of OH is the same as NaOH because it's a strong base. So there's the concentration of NaOH, dilution calculations, and again, and again we find that it comes out to this number. And so these here are the two concentrations. This one here of H3O, and this one here of OH. Oh, that's my phone ringing. Just a second. Okay, that was actually Mr. Ruberg. Huh, fun. Okay, so here we have two concentrations, one of H3O and one of OH, and we'll look and see. Shoot, did it again. We'll look and see how these can be found to find the pH now. And so the next step in this example is to figure out which ion is in excess. And so that's pretty easy because we have the two concentrations. You can see the two numbers, and you assume all of the others are used up, okay? And you take a look at the concentration. So obviously OH in this case is in excess because it had a bigger number with the 0.15. So then what you have to do is figure out, okay, well, how much is it in excess by? So you can see that you're going to end up subtracting here, and we're going to take the OH at the start and the H3O at the start, and that would be these two numbers, the concentrations of them. And this is the concentration left over of OH. Okay, so now you have to take that number, because technically remember that when an OH ion and an H3O ion meet up, that they will again form water according to the equilibrium. So they kind of nullify each other. So by figuring out their concentrations and subtracting them, we are going to find that this is the resulting OH concentration. Now the third step in this process is to take the concentration of that of that OH and convert it into pH or POH. Now because OH was in excess, we have to take the POH of it. You can't go from concentration of OH to pH right away. Okay, so you can do it in two steps, but the step I'm going to take is take the POH and then just take the 14 minus and get the pH. So again, the negative log of the concentration of hydroxide, we saw this last day, to get the POH. And then I'm going to put the concentration in there of 0.01225 molar. Don't forget that it's negative, and so that's why we times it by a negative number, and there's our POH. It's 1.9. That means that the OH is actually quite strong. So this is quite a basic solution. So to find the pH of that, again, we take 14 minus that number, and there's our pH, a pH of 12. So quite a strong, quite a high pH, very basic solution. Okay. So again, we just sort of figured out, hey, what's the concentration of this? What's the concentration of that? Of pH and of H and OH, H3O and OH. Subtract them to find your final concentration, and then do your POH or pH work at the very end once you know the excess concentration. Okay, so in a second example, let's take a little bit of a different approach and throw moles into it. So we are going to, here's the question, how many moles, where's the question? There's the question. How many moles of hydrochloric acid have to be added? Here it gives us a volume of a solution, it gives us a pH, and we want to set, we have a target pH now of 7.25. And so the reason why it's assumed no volume change, because this turns into a calculus question if you start dumping it in there, because when you dump in the HCl, the volume actually increases a little bit, and we don't want to do calculus in chemistry 12. So let's just assume no volume change. So both start and final pHs are greater than 7. So because we're starting with the pH greater than 7 and we're ending with a pH greater than 7, it's actually going to be easier if we find the concentration of OH at the start and at the end and work with POH. Okay, so we're going to attack this question from the POH standpoint. So we're going to take these pHs and we're going to turn them into POHs by going 14 minus. Okay, so here's the first one, 14 minus the pH. The first one it comes out with a POH of 5.588, and the second one comes out with a POH of 6.75. So now that I have the POHs, I can actually calculate the concentration of H's easier this way, right? Because it's easier to go this way through the through the pH loop than it is going through the KW road. So I just decided to do the 14 minus instead. So the concentration of OH at the start, again, we're going to anti-log that number, and you get this. And then the concentration of OH at the end, you anti-log that number, and you're going to come up with this. So this is the difference that we want in the concentration of the OHs. Okay, so we're going to start here. We want it to end there. So you can see the concentration of OH going down. This is 10 to the negative 6. That's 10 to the negative 7. So if the concentration of OH is going to go down, then we need to know how much H3O we're going to start with, right? So let's put it in a little formula like this. The final OH concentration, see that, should be equal to what you start with the OH and then take away, remember that this is 1-to-1, so take away some starting acid amount. So using this formula where the final OH will be equal to the start, but then you take away how much acid we're going to add, you do this. You put in your numbers here, okay, and you solve for H3O. And so in this case, I'm going to just rearrange this equation. So the starting H2O, again, all I did was subtract 1.78 from both sides, times 10 to the negative 7. You do this math, watch out for your sig figs because you're subtracting, and you get 2.40 times 10 to the negative 6 molar. And that is the starting concentration of the acid, okay? But we're not done yet. Just because we know the concentration of what the acid should be, we still don't know how much to actually put in. So at this point, we are going to factor in the fact that we have 1,250 liters of this acid. And then again, you just bring that in to cancel off the liters, and you find that it's actually 3.01 times 10 to the negative 3 moles. So this is like an enormous fish tank, and you're throwing in, like a cupful of acid to lower the pH. So, well, 1,250 liters, yeah, that's not a really big pool, but it's the same concept about a pool, but they do all the chemical calculation for you at the pool store as to how much to add, or on the side of the bottle there. Anyway, so hopefully that made sense. Again, more of the pH loop using, but in this case, just comparing the acid to the base and figuring out which is in excess first. That's sort of an added little bonus there. Also changing the pH and figuring out how much, what's the concentration of how much we have to change the concentration in order to modify the pH to whatever we want. Okay, so do exercise 59 to 67, just do odd numbers, and also we're going to get into the review for test 6 if you have enough time. So again, the review will be tomorrow and the test is going to be the following day. So hopefully everything's going great for you. Okay, bye-bye.